Hi, it's Ms. Moser, and I'd like to talk to you about something very serious: inertia and mass. As we've discussed, inertia is just an object's tendency to resist changes in its motion. Sometimes stated as an object at rest stays at rest, an object in motion stays in motion. And pretty much the center of Newton's first law. So what does that have to do with mass? Well, quite a lot, as it turns out. Imagine two objects. Oh, let's say a lead brick and a ping pong ball. Now, if you take a stick, pick your stick, golf club, baseball bat, 2x4, don't care, and you hit each of these objects with equal force, one of them is going to accelerate out of the park, while one of them is just going to move a little bit. Which one's going to accelerate at a tremendous velocity? Glad you asked. Well, of course, it's the light one. It's the one with very low mass. The heavier object, the lead brick, isn't going to experience much acceleration. In fact, inertia is directly proportional for mass. The more massive an object is, the greater its resistance to changing its motion. Okay, that seems easy enough. So this restates most of what we've just said. But the key thing here is that inertia is actually used every day, and you've experienced inertial systems. The big one that you would have experienced is a seat belt brake. When you continue your motion, even though the car has stopped, the seat belt, which is crossing your body, interacts with a little clutch down here. And when that seat belt is pulled forward rapidly, it stops your body from moving forward through the use of an inertial brake. The same thing are used in trailer brakes, and we can look for some pictures of those. So now this leads us to talking about equilibrium. If something is moving with constant velocity, or it's at rest, we call that a state of equilibrium. Oops. Equilibrium meaning all things are equal. Well, the net force on an object at equilibrium is 0. Easiest calculation you'll ever do. An object is at rest. What are the net forces on it? 0. They all cancel out. If something's not moving, all those forces must cancel out. Now, it's well and good for us to say, hey, it's at equilibrium, great, everything's equal and it's all 0. But to prove that mathematically, we have to use our sum of forces. So, this is where you dig out your old sigma fx, sigma fy, and prove that an object is at equilibrium. If you're not sure if an object is at equilibrium or not, the only way to determine that is by doing a sum of forces on each axis, resolving any vectors that don't lie directly on the axis, and proceeding as usual with summing the vectors. So we've talked about Newton's first law, the law of inertia. Now we're going to briefly talk about Newton's second and third laws. But we're going to start off with Newton number 2. So this is a concept that you may remember from physical science. Force is directly proportional to mass times acceleration. When the product of mass and acceleration goes up, force goes up. When the force used goes up, the product of mass and acceleration times the product of mass times acceleration goes up. Directly proportional. So, that's right, good old simple F equals ma. A is acceleration, m is mass. The important part to note is that this is the sum of the forces. So we've made it a little bit more complicated than it was when you were little freshmen. We're saying that the net force, the sum of all the forces acting on an object, is going to be equal to its mass times its acceleration. Because of this relationship, we can now look at an object that is not at equilibrium, that actually is experiencing acceleration in one direction or another, and determine either what force caused that acceleration, or what the mass of the object is, or if we know the force and the mass, we can determine how much acceleration the object will experience. We'll look at sample problem 4b on page 137 together. In the problem, we're told that Roberto and Laura are studying across from each other at a wide table. Laura slides a 2.2 kilogram book towards Roberto, If the net external force acting on the book is 2.6 newtons to the right, what's the book's acceleration? So I've listed a couple of variables here, and here's something interesting in this problem. We know that there are more forces than whatever this force to the right is. We know that there has to be a force of gravity, there has to be a normal force, badly drawn, and there was the force of Laura's push. We'll call that the force of Laura. There would also, we haven't really talked about it yet, but there would also be a force of friction that's opposing the motion of the book. But in this case, they've done the work for you, and they've already figured out that the net force on the book is 2.6 newtons to the right. So what does that leave us with? Well, good old F equals ma. This is pretty easy. We're solving for acceleration, so we're just going to divide both sides by m. Force divided by mass equals acceleration. We don't have to do the sum of forces, like I said, because the work was done for us. When we compute, we get a raw value of 1.1818, etc., etc. It continues. Now, what units would we have? Well, remember your dimensional analysis, that a newton is 1 kilogram meter per second squared. So we've just divided out the kilogram, so what we're left with is meters per second squared, which of course happen to be the correct units for acceleration. We have two sig figs. This would be 1.2 newtons, 1.2 meters per second squared to the right, and we do need to specify direction because acceleration is a vector. That's a really easy one. Let's do one together that's a little bit tougher. And one quick note, realize that I did not in fact draw a free body diagram here. So if I get rid of the table, I approach a free body diagram, though I'm not really labeling all the forces because I wasn't given all the forces. So that was more for demonstration's sake than anything else. Okay, let's do one more of these type of problems. I have a force of tension problem for you. So here I have an object. Let's say it's a box. It could be anything. And let's say it's got a mass of 15 kilograms. Now, this box is hanging by a cable, but it's not just hanging here. We actually want to achieve an upward acceleration of 3.0 meters per second squared on the box. We want to speed this thing up until we get it up to some speed. Who knows what that is? So the question is, how do we figure out the force of tension that's required to accelerate this object up towards the ceiling? This could be something in a theater, this could be a curtain being pulled up, or just about anything else you care to imagine. Alright, so let's go back to our basic equation, and that's that the sum of forces, or the net force on the object, is going to be equal to its mass times acceleration. Well, one of the things, we have mass and acceleration. What we don't have is net force. So we're going to have to find net force using what we know about gravity and force of tensions. And the easiest way to do that is to actually put it in line with this entire thing. So we know that the net force on this object is going to be equal to the force of gravity plus the force of tension. And that the force of gravity plus the force of tension will equal the mass times the acceleration. Okay, now we're getting someplace. So at this point we can get rid of our little sigma f. We don't need it anymore because we have what we're going to be working with. Alright, what do we know about force of gravity? Well, it's equal to mg. We have the mass and we know what acceleration due to gravity is. So we can go ahead and substitute this. mg plus the force of tension is equal to the mass times the acceleration. Well, this is pretty simple. Force of tension is equal to the mass times the acceleration minus the mass times acceleration due to gravity. Okay. Well, let's put some numbers in. Okay, we've entered some numbers here. Now, you'll notice we're subtracting a negative, so we're actually adding acceleration due to gravity to the acceleration, the upward acceleration, I should put that in, that we want to achieve. We've left this acceleration as a positive number for that reason. The little dot in there is actually a multiplication dot. Okay, let's get numbers. The force of tension on this rope, if you're accelerating this box upwards at 3 meters per second, is going to be 192.15 newtons. With sig figs, and we only have 2, we'll call it 190 newtons. But either way, the important thing to note here is that this is significantly more than the force of gravity acting on the object, because when we're pulling something upwards, it's not at equilibrium. When we're actually accelerating it, we're exerting more force on it than we would be if it was just still. Okay, a couple other notes here. You could have done some fancy algebra in this step and factored out an m. You don't have to, but it's a useful trick to be aware of because there are problems where that makes all the difference. That would look like this. Force of tension, F sub t, equals m times the quantity a minus g. There come points when maybe we don't have mass and we need to find a way to get mass out into one spot so we can cancel it with something else. That's how you do it. Okay, with that, you can go ahead and get started on the 4B practice problems in your Holt Modern Physics. Those are on page 138, and numbers 1 through 5 are all assigned.